Let's talk about the bisection method, which is used for finding roots of an equation. When you were in school, no doubt you had problems like this where you would have, x squared plus 3x plus 2 equals 0, and you were told to find the roots. And for a problem like this, you'd factor it, and you get x plus 1, x plus 2 equals 0. We can check. It's x squared. 2x, 1x is 3x. 1 times 2 is 2. And then we know that x equals minus 1 and minus 2. Those are the roots. But what if we have something like this? X to the 4th power minus 8x cubed plus 14x squared plus 7 equals 0. That's not so easy to solve, right? Because this has a 4th power, and while there are technically closed form solutions for things up to the 4th power, it still wouldn't be easy to solve, okay? So we can use something like the bisection method for solving this. But also note that each of these, this expression, are examples of what we call nonlinear equations. And we can use this method for solving other types of nonlinear equations. For example, if we had e to the minus x equals x, and we want to solve for the x that satisfies that, what we can do is rewrite this as e to the minus x equals 0. Now it's a root finding problem. Right? Just like this is a root finding problem, this is a root finding problem, this is a root finding problem. We also could use it for things like if y is equal to the cube root of 7, we can rewrite this as y cubed is equal to 7, and then y cubed minus 7 equals 0, and that's also a root finding problem. So this same method can solve or be used to solve problems that on the surface don't appear to be about finding roots. We just have to think about the problem differently. So what's the underlying idea here? Well, let's say that we have, this is the x-axis, and we have this function, f. And so here we have a, and this point right here would be f of a, and then we have b, and this point is f of b. So what we do, and this would be r, which would be the actual root, what we can do is find the midpoint of this, and we'll say it's approximately here. So what do we note about this? Well, one thing we note for the way I drew this, f of a is negative, so it's less than 0, and f of b is greater than 0 because it's positive. So we can find the midpoint, and in this case, this would be f of m, which is also negative. So what we'll do is we'll move a to here. So this is a new a, because these are brackets. And then now we find a new midpoint. Let's say it's here, and that looks like it's on the same side as f of b because there's f of m. This would be the new m. Well, now we move b to here. And we just keep doing this, tightening it up till we get closer and closer. And we'll stop when we reach some level of tolerance between the two different numbers. If the true answer was 3.001, maybe what we get is 2.999, and over here we have 3.003. And if that is the level of tolerance where we want to stop, we would know that the answer is in here somewhere. Because this is an example of what we call a numerical method. And one of the things to keep in mind for many numerical methods is they may not spit out what you think of as an exact answer. Instead, they use some iterative process, is what we're using here. We go from here to here to here to here to here, and just keep going until we get close enough. And so if I want a better answer, then I just say, well, don't stop at this many decimal places. Go out to 7 decimal places or 10 decimal places or whatever. So that's the underlying idea. So let's look at a Python program that I wrote that will solve this for us. So here's Python. I'm using the NumPy library because it's going to use this sine function down here. But this right here is the actual algorithm. So I passed in, just to talk about the function for a moment, I passed in the function for the problem to solve. I pass in the interval A and B and then what level of tolerance I want to use. And so what this does is says while the difference between B and A is greater than that level of tolerance, which is basically, you know, how many decimal places I want to go out to, I'm going to find the midpoint. Notice the way I found the midpoint is this way right here. Now, many authors will use this expression, and that will work, but the potential problem with this is one of overflow or underflow. Imagine that the largest number that I can store is 2 billion. Well, if A and B are both very close to 2 billion, like 1.9 billion each, or approximately that, it wouldn't ever be the same number for this type of approach. But let's say they're both approximately 1.9 billion. Well, if I add those together, I get an answer that's approximately 3.8 billion, which is greater than 2 billion, and therefore I can't represent it as a number. So I have an overflow problem that way. And if they both had been negative numbers that were very large in magnitude, like negative 1.9 billion and negative 1.9 billion, well, now I can have underflow. So this approach reduces the opportunity to have overflow or underflow. Okay? Here's where I calculate f of A and f of M. Now, technically, I don't need to calculate f of B, but I included it so that when we look at the results over here, we can see what's happening with the function values. Here's where we decide which bracket to move in. So notice I'm getting the sign, and I say if the sign of f of A is equal to the sign of f of M, well, A moves over to wherever M was at. Otherwise, B is the one that moves in. Now, many authors will use this approach right here, because if A and B are on two different sides of the x-axis, then they should have different signs, and therefore their product should be less than 0. Well, once again, we have a potential problem here. In this case, we have a problem with underflow, because think about it, as we get closer and closer to the x-axis, f of A and f of B both will get closer and closer to 0. And so if we multiply two very small numbers by each other, we get a much, much smaller number. And therefore we have a chance of producing a number that's too small for us to represent. And so this is just here for printing out some stuff. The count I here is just here as a counter so we can see how many iterations it took. And then we just keep cycling, like I said, as long as the difference between B and A, our interval values, are greater than some tolerance. Let's look and see what function I'm processing here. So here we have e to the negative x power is equal to x. And so this is a comment in Python. And so I'm using the NumPy exponential function. And so here I rewrote this as a root finding problem. So e to the negative x power minus x is what we're solving. So let's go down to here. That's one function. Then we'll look at this function. Then we'll look at a third function in a moment. So I'm passing in the function name. Python lets me do that so that way I can write my bisection algorithm in a generic fashion. I just call it f as the function. 0 and 1 are my initial interval values, my A and B, and then this is my tolerance, 10 times, or 10 to the negative 6th power, or 1 times 10 to the negative 6th power is the way this is written. Okay. So here we can see we start off with our initial interval, and then I calculate the function values. Once again, we don't need this column, but I use it to see what's happening. But here's the midpoint of those. Not M, but the function value of the midpoint, which is what we actually need. M itself is not what we need. We need the function at that value. And so we see the difference between B and A now will be this. And then we're going to move in. It looks like, so B is the one that moved in because B and, right here we can see B and F of M, or excuse me, F of B and F of M are the same sign. So these move in. So first A shifted in, now B is shifting in. Looks like B shifts in again, And we keep doing this, and notice we're getting closer and closer. Because here's our approximation. Like at this point, we say that the answer is between 0.5625 and 0.57033125. So here's the difference. And we get closer and closer, and eventually we get down to our tolerance right here. And so we know the answer is between these. So these are the same out to, there's 56714, 56714. These are the same values out to 5 decimal places. So what's the answer that we use? Well, some people will just take the midpoint of these two values because that's really the way we would shift in the next time anyway on the next interval. Another way would be say, well, just pick the values that they agree on. They both agree to this point, and they can never get worse. They just keep getting closer and closer. And so you could say that the solution to 5 decimal places is 0.56714. Okay? Let's do the cube root problem. Now, before we move on, though, let me say, well, how did I know what interval to use? Well, one of the things I did was, because I didn't know the actual answers, I looked at this and said, well, e to some power can never be negative. So if I were to choose x was a negative number, I would have to say e to some power somehow becomes a negative number in the original problem, and that can't be. So I knew the left bound had to be 0, and just playing around with some numbers, I knew it probably was less than 1. So that's why I started with that. Let's try to find the cube root of 7. So now we'll comment out this and rerun it. So now what would the bounds be on this? Well, the cube root of 8 is 2. So the cube root of 7 has to be less than 2. But the cube root of 1 would be 1. So it has to be greater than 1 but less than 2. That's how I know what bounds to use here. So let's run this. And we go through the same process, and we see we get down here to 1.91293 is where they're both the same. And if you try that, you'll see that raising that to the third power will be pretty close to 7. Okay. And then let's use one more. This one is something we can easily solve for because the roots were just 3 and 8, so this should make a believer out of you. But you would get it in this form, x squared minus 11x plus 24. So now we're going to solve this and run it. Let's see what happens. Well, even though we know one of the answers is 3, notice I don't get 3. Because remember what I said in the beginning. These are just brackets, and we get closer and closer, but we may never get the answer in an exact form like you think it should be. We're just cutting the distance between the two brackets in half every time. Now, another thing that's interesting about this is I started with values such that they're both positive and negative, but what would happen if I did, say this? What if I said, since the roots are 3 and 8, what if I said 2 and 9 as the values? Let's see what happens. Well, they're both lead to positive function values, but notice that once I find the midpoint, because there's actually 2 roots in this range, once that happens, well, then I start getting that f of a and f of b are on different sides of the x-axis. And so it still can find 3. Now, what if we chose something where it wasn't correct? What if we said, I think the answer is between 20 and 29? What happens? Well, the algorithm itself still tries to find midpoints, but look at what happened. F of A is positive, F of B is positive. Here's F of A is positive, F of B is positive. They never get on opposite sides of the x-axis. So that's sort of my way of knowing something's going on here. Even though these two answers are close, they have to be close because of the way the algorithm works. The algorithm can't know that this is wrong necessarily, but the way some people would write the algorithm is they actually will check at the very beginning to see if f of a and f of b are of different signs. If they're not, then the algorithm will just stop at that point. But as I showed you with the previous value of 2 and 9, You could have values where f of a and f of b are initially on the same side of the x-axis and still get the correct answer. But notice here they never get on opposite sides, which is my clue that something here was wrong. Okay? So, what are some other comments? So, the downside of this approach is it's slow as compared to some other approaches. It doesn't incorporate any information about the function itself into the process. Like, there are methods that will look at the slope of the function and use that to try to get to the answer faster. Okay, but this doesn't use that kind of information, so it's slow. On the other hand, if the value r, our root, is in our interval a to b, then it's guaranteed to find the answer, or find an answer that's within your interval. That's pretty close. Okay, so let's call this one observation. Another one is the number of iterations is equal to the ceiling. Sorry, I speak fluent Texan, so you may have thought I said something else, but the ceiling function here, this is log base 2 of b minus a over your tolerance level. Okay, so this will let you decide in advance how many iterations you're going to run. Okay, if you make your tolerance level better in the sense that it's even smaller, number of iterations will go up. A third thing is that the solution error that is, if we have the midpoint minus the root, the true root, that is the true answer, and the absolute value be less than b minus a divided by 2 to the n plus 1 power, where n equals number of iterations. Okay, so that's the bisection method, and as we saw, it's fairly easy to implement, and it's also fairly easy to understand the answer, I think.